Particle kinematics. We are going to continue our discussion with normal and tangential components in this video. So as you know, there are three kinds of coordinate system. We did Cartesian coordinate system before, which is rectangular coordinate system. Now we are going to learn normal and tangential components, and then later we will learn about cylindrical components or polar coordinate system. So here in Cartesian coordinate system, our origin is fixed, x, y, z. We measure it from the origin. So origin is fixed and particle is moving. With normal and tangential component, our origin moves with a particle. So it's not fixed, it moves along a particle, and that's how we are going to deal with this curve motion. So many times, if a particle is taking a curve, and if we know equation of the curve, and if we know the radius, if we have that information, it is convenient to describe the motion using n and t coordinates. That's called normal and tangential coordinates. And that's what we do in this curvilinear motion in this part. So in order to use that tangential n and t coordinate system, we need to know radius rho. And this radius will be different at any given point. So at this point, at this point, at this point, this radius will be different. And we need to know equation of the curve, we need to know radius, and if we know that, we can use normal and tangential components. The velocity in normal and tangential component is given by v, u, t. Now in Cartesian coordinate system we use I, j, k. Here we use ut and un. Ut is for tangential component and un is for normal component. So that's how we can write down velocities v, ut, and v is nothing but magnitude of that velocity. However, the most important part in normal and tangential component is acceleration. Let's say we have a particle, it's going like this, and then when it's taking a turn, it's speeding up. Let's assume that it's speeding up and it's increasing in acceleration. If that's the case, this is the direction of its acceleration, and its acceleration will have two components, normal component and tangential component. This normal component also known as centripetal acceleration. So normal component is towards the center, wherever at that instant, wherever the center of the curve will be at that point, that towards that we will have normal component, and tangent to the curve we will have tangential component. And most of the time, whenever you deal with these problems, normal and tangential component, we are more interested in this acceleration part. It means you have to do calculation for acceleration. You have to find out what is normal component, you have to find out tangential component of acceleration, and once you have that, you can use this Pythagoras, at square plus an square, and then you can find out its actual acceleration. So that's the general idea. You have to figure out what is at, what is an, and once you know that, you can calculate acceleration. Now without going much detail into mathematics, all you need to know is the definition or formula for tangential and normal component. So tangential component is given by v dot. V dot is nothing but dv by dt. This is your regular velocity, derivative of velocity dv by dt. And normal component is given by v square by rho. Rho is the radius of a curvature and v is your magnitude of velocity. Now let's assume that you are driving in a straight line. When you do drive in a straight line, if you are not taking a curve, in that case an will be 0. The reason is that if it is a straight line, then radius of a straight line is infinity, and if this is infinity, an will become 0. Anything by infinity is 0, so an will become 0. So even if you are driving in straight line, normal acceleration is there, but the value is 0. However, as soon as you start taking a turn, this will come into picture, because there will be some radius, there will be some velocity. Now this at is something that if you are driving in straight line and if you push on accelerator, if you are speeding up, then you pushed back in your seat. That's what you feel is tangential acceleration. Same thing with normal acceleration. If you are taking a very sharp turn, and if you are taking a sharp turn at left, you move to the right. If you're taking sharp turn to the right, you will move to the left. Whatever you feel that's nothing but your normal acceleration. So whenever you drive next time, see if you can feel this normal component of acceleration. Another thing is normal component of acceleration is always positive. This at could be negative. If you are slowing down, that's called deceleration. In that case, this tangential acceleration could be negative. But as far as an is concerned, it cannot be negative. It is always positive. Reason is that v square, it is a square, it is going to be always positive. And radius is also going to be always positive. So an is going to be always positive. So keep that in mind. Whenever you take a turn, whenever any particle takes a turn, we will have two components for acceleration, normal component and tangential component. Tangential component is to something that you experience when you speed up in your straight line. This is a regular acceleration. And normal component, when you start taking a curve, you will experience this normal component of acceleration an. It's given by v square by rho. Higher the velocity, lower the radius, higher the value of an, and that's how we can find out. This is very important formula, v square by rho, keep it in mind. And the normal component is a tangential component will be simply dv by dt. Now let's directly do a problem and let's see if we can figure out this normal and tangential component. Now we have a particle, a boat, and it's taking a curve. So this is a boat we have here, and this is going to take a curve like this. It's going to follow a curved path like this. So this is a semicircular path it's following, and its radius is 40 meters. So the boat starts somewhere here, and then it's going to continue like this, and when it starts here, velocity for this profile is given by v is equal to 0.0625 t square. It means that velocity is increasing with respect to time. When time was 0, velocity was 0. When time 1 second, velocity increased. 2 seconds, 3 seconds, 4 seconds, velocity continued to increase. And then it's going to reach here at 10-second mark. Now it's going to continue, but after 10 seconds, it's here. Now what it says is that velocity is given. Determine the magnitude of acceleration when t is equal to 10 seconds. So velocity is increasing, but at 10-second mark we are going to freeze the frame, and at that point I want to find out its acceleration. And that's the problem. What is its acceleration? If velocity is increasing with this profile, the equation is given. What is the acceleration at 10-second mark? Now to calculate that acceleration, as it is taking a curve, it will have two components, tangential component and normal component. So if we somehow can find out tangential and normal component, we can solve this problem by using this formula. So to calculate first tangential component, we are going to use this part. At is equal to v dot. V dot is nothing but dv by dt. Now we have this equation, we have v. If we differentiate it with time, we'll get v dot, and that will be nothing but your at. So all you have to do is differentiate this thing with time, which is very simple. 0.0625 t square will become 2t, that will be 0.0625 into 2t, that will be dv by dt, and in that you will put t is equal to 10 seconds. If you do that, you will get value of 1.25 meter per second square, and that will be your value for tangential acceleration. So here this value at is 1.25 meter per second square. Once you are done with this value, we need to know value for an. An is given by v square by rho. Now velocity we have to find out. Radius already given 40 meters, so we have radius. So velocity here, to find out velocity at 10-second mark, we are going to use this equation. All you have to do is put t is equal to 10, and we will know exact velocity at 10-second mark. So see 0.0625 into t 10 square, that will be 100, and whatever that velocity, take that velocity here, v square divided by 40, that's radius, and then you will get value for normal acceleration as 0.9765 meter per second square, and that's the value. So normal component will be 0.9765 meter per second square. I have at, I have an. I'm going to use this equation Pythagoras, and then I'm going to kind of value for a, and that value will be 1.59 meter per second square, and that's how we can find out. That's how we can use this equation. All you need to know is these formulas, and then you can find out anything that is taking a curve, you can find out its acceleration. Let's do another similar problem. Now in this problem, instead of boat, we have a car taking a turn. So it's taking a turn on this path, and what we have is the angle. So this is a tangential component at that point A, this is a normal component, and what we know is that tangential component making an angle of 30 degree to its acceleration, whatever its acceleration at that instant is. What else we have is the speed is 80 feet per second at point A. It means this car is going like this, but when it comes here at that instant, the speed is 80 feet per second. Now unit is in feet, so keep that in mind. 80 feet per second is moving like this. We have speed and we have magnitude of its acceleration 10 feet per second square. We also know this part. The magnitude of this acceleration is 10 feet per second square. So that value is given. So it means we have velocity, we have acceleration. What we want to find out is radius of curvature. We want to know what is the radius of curvature for this road, wherever this, whatever the center point, what is the radius. And you also want to know tangential component of acceleration. So you want to know this tangential component of acceleration. The information we have this angle and we are going to use that. So first, to find out radius, we are going to use this formula an v square by rho. We have velocity 80. We have to find out radius. In order to find out radius, we have to find out what is an. An is simple. An, based on the geometry, I can say an is equal to a sine 30 or a cos 60, whatever. If this angle is, then a cos 60, this angle is a sine 30. So I'm going to take that a sine 30 is equal to 5. A is nothing but acceleration is 10. So 10 sine 30 will be 5 feet per second square. That's the value for an. So this is the value an will be 5 feet per second square. And once you have that phi, you're going to put this phi here, and then you will get value for radius. So velocity we know 80 square, an we know 5, and we take rho here, we take a divided by an, and then we can find out radius is around 1280 feet. So if you do this calculation, you will get the answer. So total radius here is 1280 feet. And once you have that, tangential component is simple, a cos 60. So whatever value 10 cos a cos 30, 10 cos 30. So this is the angle 30. So 10 cos 30 will be my tangential component, and the value will be around 8.66 feet per second square. It's a very simple problem. All you have to remember these formulas, and then you can solve this one. So that's one problem. Now let's do another problem. This one is big one, and this is from the book. Now what we have in this problem is industrial conveyor belt, and all these boxes are going on this conveyor belt. So our box here, it starts at point A, and then as it goes ahead, velocity increases and it comes at point B. Now what it says is that it's going to travel along industrial conveyor. It starts at A, increases its speed in such that AT is equal to 0.2 t meter per second square. It means its acceleration is increasing with time. So 0.2 t, which means that when t is equal to 0, acceleration was 0. Then t is equal to 1, acceleration was 0.2. So on and so forth. So as time increased, acceleration also increased. So we have acceleration profile or equation for acceleration here. So box starts at this point, it's going to come like this with increasing velocity, and it's going to reach at point B. Now when it reaches at point B, it's going to continue, but when it reaches at point B, we are going to freeze the frame, and at that instant when it reaches at point B, I want to find out its acceleration, and that's the problem. Determine the magnitude of acceleration when it arrives at point B. So now it's going to reach here, and at that instant I want to find out its acceleration. Now as it's taking a curve here, it will have two components for acceleration. One normal acceleration towards the center, and one tangential acceleration tangent to the curve. If I can find out AT and AN, value for AT and AN, I can find out its acceleration, and that's the problem. We have to figure out what is AT, we have to figure out what is AN, and then we can calculate its magnitude of acceleration. Now to find out AT, AN, we have the formula. Normal acceleration is v square by rho. Radius we know, 2 meter radius is given. That's the radius for curvature. We have that. We don't have velocity here. Now what we have instead of velocity, we have acceleration profile 0.2 t. Based on that, we have to figure out what could be its velocity when it comes to point B. We don't know velocity at any given point, but we need particular velocity at point B. If we have that velocity, we can put that velocity here, we'll get A. We don't have that yet. And then we also need tangential component, which is nothing but dv by dt or v dot 0.2 t is given. So if somehow we know time, total time to come from here to here, if we can figure out that time here for this box from A to B, we can put that time here multiplied by 0.2, we'll have value for 80. But for now we don't know time. It means we have to solve this problem for velocity. We need to know velocity at point B, and we want to know total time for journey A to B. If we can find out velocity and time, we can get values for AN and AT. Once you have AN and AT, we can solve the problem. So now to find out velocity and time, I'm going to use this relationship. We know dv by dt is equal to 0.2 t. Now I'm going to take that dt this side and I'm going to integrate it. So dv by dt is equal to 0.2 t. So it will become dv is equal to 0.2 t dt, and I'm going to integrate it to find out relationship between velocity and time. 0 to v, that's initial velocity to final velocity, and 0 to time, initial time to final time, 0.2 t. And this is very simple integration. Once we solve this integration, what we get is v is equal to 0.1 t square. So this one will become v, this one will become t square by 2. This 0.2 will come out of integration and it will become t square by 2. 0.2 divided by 2 will become 0.1, and then you will get total value of 0.1 t square, and that's what we have. V is equal to 0.1 t square. It means now you have relationship between velocity and time. Before that you have relationship between acceleration and time. Now you know velocity and time relationship. It means that velocity increased with respect to time. So when t was 0, velocity was also 0. And then t equal to 1 second, velocity increased to 0.1, 2 seconds, 3 seconds, 4 seconds. As time goes up, velocity also went up. Now I have that relationship. But still, I don't have a number, I don't have exact value which I can put here and I can solve the problem. Now to get that, we have other information here. What we know in this problem is this is 3 meters and this is radius 2 meters quarter circle. It means we know how much distance traveled from A to B for the box. That's linear distance travel. Linear distance means if I can take a thread and then if I measure that length of that thread from A to B, that's my linear distance traveled. I know the linear distance travel, which is 3 plus this quarter circle. Circumference of a circle is 2 pi r. 2 pi r divided by 4 is circumference of quarter circle. So I can find out circumference of quarter circle. This distance plus this distance, whatever it is, that will be total distance. And based on that distance, I should be able to find out time. So here, I know v, velocity is nothing but distance upon time. And I already have equation for velocity, 0.1 t square. So what I'm going to do now, I'm going to take this 0.1 t square, I'm going to put it here. And I'm going to solve it for time and distance because I have formula for velocity. So I'm going to take that here and then it will become 0.1 t square ds by dt, and then I'm going to take this dt in this direction, in this side, and I can solve it. So if I do that, if I take this 0.1 t square here and if I take dt this side, I can rewrite this one for ds is equal to 0.1 t square v dt, 0.1 t square into dt, and I'm going to integrate it for final distance 0 to SB. This is my 0 to SB, that's my linear distance traveled, is equal to 0 to TB, that's my total time required for journey A to B. Now this is again simple integration. If you solve this one, you will get value of time. So if you want, you can pause the video, you can find out time. So here you also need to total number for SB. So SB is 3 meters plus quarter circle. Quarter circle is 2 pi r divided by 4. In this case 2 is radius, 2 pi r divided by 4. That's this length. So this length plus this length, you are going to get final length is 6.142 meters. So this length total is 6.142 meter. Now all you have to do is that 0 to 6.1 meter, ds is equal to 0 to tb 0.1 t square dt. This is a simple integration. Here integration for t square is t cube by 3, and then once you do that you will get this numbers 6.142 meter is equal to 0.03 tb cube, and if you solve this one you will get total time is around 5.69 seconds. It simply means it required from A to B 5.69 seconds. It starts at t is equal to 0 second, and then within 5.69 seconds it came to point B. Now once you have the time, you can take that time, you can put here, you will get velocity. Once you have that velocity, you can put that velocity here, you will get value for an. It's very simple. And then once you have that velocity, once you have that time here 5.69, you can take it here 5.69 into 0.2, you will get 80. Once you have that value for an and 80, you can put those values here, then you will get value for a, and you can solve the problem. So if you want, you can pause the video and you can go ahead to get values for an and 80. Now here with 5.69 time, you will get velocity at point B is 3.23 meter per second. Then you will get normal acceleration, v square by rho is around, that's 3.2 square divided by radius is 2 meter. If you do that, you will get 5.242 meter per second square, and then you will get tangential acceleration 1.138 meter per second square, which is nothing but we have to put this time here. You have to put this time here, and then you will get value for 80, 1.138. Once you have 80 and an, you can put it here, and then you will get final answer as 5.36 meter per second square. So this one 5.24 meter per second square, this one tangential 1.138, and this acceleration will come around 5.36 meter per second square, and that's how you can solve the problem. Now this one is solved problem from the book. When you study for exam, change some of the numbers, change this length, or change this equation. Instead of 0.2 t, think about it if what if it is 0.1 t or 0.3 t. Change this equation and see how your answer will change, so you can practice that way. So that's the problem for normal and tangential component. We will do one more. We will do two more problems. So one problem is we have this sled here or toboggan. It's coming down this slope, and when it is coming down this slope, it reaches at point A here, and it's going to still come down. It will start somewhere here. It's going to come down, but when it reaches at point A, its speed is 10 meter per second is given. So at that instant 10 meter per second, and its acceleration is given, v is equal to 3 meter per second square. That's its acceleration. That's your tangential acceleration at this point. So tangential acceleration and velocity is given. Our objective is to find out its total acceleration. It means we want to know value for an. At is given. If we just calculate an, we can find out a. At is 3. We have the value. So our objective here is to find out an. To calculate an, we need rho. Velocity we already have it here. 10 meter per second velocity we have. We need rho, radius of a curvature. So this is a curve path, and somewhere there we have radius at long distance, but we want to find out that radius. In order to find out the radius, we are going to use this part. We have the equation for the curve is 0.01 x square. I'm going to use that part, and then to find out radius, this is the equation that is normally used. This equation is 1 is equal to dy by dx square 3 by 2 and divided by double derivative of this equation. So here I have the equation y is equal to 0.01 x square. I am going to find out single derivative, which is very easy. Single derivative dy by dx is nothing but this x square will become 2x, and this will become 0.02x, and that's it, 0.02x. Double derivative will become, this the derivative of this one will become just 0.02. Now I am going to take this part 0.02x, I am going to put it here. I am going to put this 0.02 here, and then I am going to find out radius at x is equal to 60 and y is equal to 36. So there is no y here, so I am going to use this x is equal to 60 here. So when you put these numbers here, put x is equal to 60 based on this geometry, and then you should be able to find the radius. So here I'm going to do this calculation. So I'm going to put that x is equal to 60 meters, and then I'll get radius of 190 meters, 190.5 meters. So this radius is somewhere at 190 meters, that the center is there for this part at point A. Once I have that radius, I'm going to take that radius here and I can find out an. Once I have that an, I'm going to calculate acceleration. So v square by rho, 10 square by rho, I will get value for an is 0.525. And once I have that value, I'm going to use that in the equation, and then I'll get final number is 3.05 meter per second square. So this is the number I'll get, is 3.05 meter per second square, and that's how I can find out. Once I know radius, I'll get value for an, and then I can find out its magnitude of acceleration at point A. Another last and similar problem we have here is a jet plane. Now what we have is the jet plane climbing up on this path. Now when it's climbing up on this path, its equation is in kilometers. Y is equal to 0.4x square. And keep in mind, this is in kilometers. So y is equal to 0.4x square. This is the equation we are going to use to find out magnitude of acceleration. So this plane is climbing up. Speed is given 200 meter per second. Increasing at rate. Acceleration is given 0.8 meter per second square. Its tangential acceleration is 0.8 meter per second square. Speed is 200 meter per second, and we have to find out magnitude of its acceleration. Which magnitude of its acceleration will be an square plus at square. At we already have 0.8. An we have to calculate. Now to calculate an, we know an is equal to v square by rho. We have velocity 200. If somehow we can figure out radius, we should be able to find out an. So to find out radius, we use same equation. So here radius is equal to 1 plus dy by dx, single derivative square raised to 3 by 2 divided by double derivative of that equation. So the equation we have is y is equal to 0.4x square km. So it should be written km, kilometers. So keep that in mind. So this is in kilometers, y and x are in kilometers. So this is going to be in kilometer equation. So what we are going to do is we are going to find out single derivative of this equation, and then double derivative. We are going to put these numbers there, and then we are going to find out radius. So single derivative of this one will be simply 0.8x, and double derivative will be simply 0.8. It's very simple. Now I'm going to take that 0.8x here and 0.8 here, and once I do that, I'm going to put x is equal to 5 kilometer. Keep in mind these equations are in kilometers, so I'm going to put this 5 kilometer here, and then I'm going to solve this thing. And once I solve it, I'll get the value of radius. I can put that radius here. I'll get normal acceleration. So when we solve with this one, 1 plus 0.8x, that's single derivative, and here 0.8, that's double derivative. So x is equal to 5. I'm going to put that 5, and then I'll get a value in kilometers. Because this equation was in kilometers, I'll get radius is in kilometers. So 87.62 kilometers. So somewhere at 87 kilometers, I have the radius for this point. Now, whenever you use this number here, keep in mind velocity is in meter per second, and therefore this rho should be in meters. So I'm going to convert that 87 kilometers into meter. It will be 87,620 meters. So I'm going to take these numbers in meter, 87,620. I'm going to put that number here, radius, 200 square divided by 87,620. You'll get value for an. Once you have an, you can take that an here and you can solve the problem. So here I'm going to use that 200 divided by 87,620. You'll get an as 0.456 meter per second square. Once you have that 0.456, I'm going to put it here, and then I'll get final answer A is equal to 0.921 meter per second square. So magnitude of acceleration at this point is 0.921 meter per second square, and that's it. The only thing in this problem is this equation is in kilometers. Keep that in mind. If it is in meter, then it will change. It will be y is equal to 0.0004 x square meters. In that case, you will get same answer. So keep that in mind. You will get radius in kilometer, convert it into meter, use it, and then find your acceleration 0.921 meter per second square. And that's it for normal and tangential component. In our next video, we will continue with curvilinear motion, cylindrical components, or polar coordinate system. That's all for today. Thank you.